Hello my dears, how are you all? So today we are going to discuss about a new session. We already completed the power system, so now we are going to move electronics. It contains both analog and digital electronics. So now we are moving by looking the syllabus of the sub-engineer. Okay, so it is one of the important syllabus, topic in KSEB sub-engineer examination. So topic wise topic I will take electronics, electrical heating, electrical wiring, etc, etc. So many topics are there. So under so many subtopics are also there. So we will now onwards we will more focus towards the KSEB sub-engineer. Normally we did so many subjects like machines, power system, and AC and DC machine, okay, and mainly the circuits. So which contains almost very basics of all which is required for the KSEB sub-engineer. And now we are more focusing on KSEB sub-engineer examination, so that each and every minute topic also we will going to cover. Okay, so first of all we are going to discuss about op-amps. See, I can take directly from the BJT, common emitter, common mode, common collector configuration and all. It is actually, it's very well. It is you already studied in +2. You already studied in BTech first year. You studied as the basic of analog electronics in S3 or S5. So now need to do that, right? Now questions will be asked from that section, BJT and its characteristics. It will not, but certain things are there, we will cover that. Not from the very basic diffusion and how the depletion layer is formed, what is the equation for diode current, etc, etc, p-n junction, n-type, p-type semiconductor. It's all basic. We don't want to waste our time because syllabus is very lengthy actually for KSEB sub-engineer. So if we can directly move into this topic, it's very important topic. A short question will be expected from the common mode rejection ratio related problem, CMRR rate. Every question paper if you took, every question paper you refer regarding the electrical engineering stream, you will definitely see a question CMRR related, common mode rejection ratio related. Okay, that all we will cover under the op-amp. Don't worry, we will grab everything. So first of all, what do you mean by op-amp? What is mean by op-amp, my dear? So normally op-amp means it consists of, it is actually a form of differential amplifier. It is a form of what, my dear? Differential amplifier. Differential amplifier. So amplifier is what? Amplifier is what, my dears? Amplifier means whatever the input we are giving, it amplifies and it gives the output. That is called the amplifier. So operational amplifier means it is basically a differential amplifier. So differential amplifier is nothing but it gives the what? Difference in input. It gives the difference in input. So normally op-amps are built from so many transistors which are connected in some particular manner, and normally that whole connection, if you show every time, it will be a very complicated diagram. So we will use a specific a diagram for representing an op-amp IC. Okay, so why the name op-amp means these op-amps are used for the mathematical operation like addition, subtraction, integration, differentiation, logarithmic or anti-log, etc. So its function is more and more actually. So why the name op-amp means it is used for the mathematical operation purpose. Before the invention of this advanced electrical network, advanced digital network, Now it is all digital control, right? So now it is controlled by digital circuit, but before we were used a digital circuit, so there you only depend upon the analog circuit. So by using op-amp only, these type of mathematical operation can be done before so many years, but now it is all give away the path to digital circuit, so no issue. So digital circuits will solve everything now, but previously we are using the op-amps for this mathematical function, and still it is a versatile device. Actually op-amp is a versatile device because still it is used for so many digital circuit. We are using it, even though the digital circuits also there, but along with that we are using these op-amps also. In digital circuits also we are utilizing op-amps in many ways. Okay, so this is also a versatile device, that's why it's called a versatile device. So this is the symbol of an op-amp here. This is a symbol of an op-amp, IC741. Normally IC741 is called, it's an op-amp, basic op-amp. Okay, basic op-amp IC is called IC741. So this is the symbol. This is a symbol of an op-amp, which means it consists of two inputs, my dear. It consists of two input. One input is called inverting non-inverting input, and the other is called inverting input. And these two are nothing but supply. This is our output. This is our output. So these are the terminals. So it is a two input and one output producing device, right? Two input and one output producing device. This plus V and minus V are for supply. In order the operation of the BJTs inside it, we need some supplies, right? We need supplies. So that supply is that biasing voltage, correct? It is the biasing voltage. So in this, see, two inputs are there, my dears. One is called a non-inverting input, it is called a plus, and one is called inverting input. That means if you are giving some supply, suppose here is 5 and here is 3, it is taken to be as minus 3 in the it as the input side, it is taken to be as plus input as to the input of the BJT. That is why it is inverting and a non-inverting terminal. And this is the simple structure of the op-amp. Okay, and its input and output relationship will be, my dears, I will explain that also. Transfer characteristics. Transfer characteristics of a op-amp. This is output and this is the difference in input. Okay, before that I will tell you one thing. What will be the output? I will tell you. The characteristics also. Then later we will talk about these transfer characteristics. Okay, so the output of an op-amp will be equal to nothing but V0 will be equal to A times V1 minus V2, where A is nothing but open loop gain. Normally we know that whenever an amplifier we are using, the amplifier will produce what? The output, which is nothing but the amplified version of the input. Now the input is nothing but the difference in the input quantities, that is V1 and V2. That is the input. Okay, which is also we can write like A into VD. A into VD, where VD is nothing but the differential input. Differential input means I already told you that whenever we are giving two input, it takes the difference of those two as the input actually. So V1 is the positive and V2 is negative. So V1 minus V2 will be the difference in input, and it will produce the output as V0 equal to A into V1 minus V2, or simply V0 is equal to A into VD, where A is called the open loop gain. A called the open loop gain. Normally, my dears, normally A have in the range of 10 raised to pi to 10 raised to 6. Normally A have the range of 10 raised to 5 to 10 raised to 6. That means if you are giving an input, suppose you assume we gave to V1 as 2 and V2 as 1 volt. Okay, you imagine. So what will be the output here now? V0 will be equal to what? A into, that is 10 raised to 6 into what is as 2 minus 1, which is equal to 10 raised to 6 volt, which is equal to 1 megavolt. So if you give 1 volt as input, if it produce 1 megavolt at output means, is it practically possible? No, it's not practically possible, because we give just 1 volt, it produce 1 megavolt. That is a very unstable system and it will not exist actually. It will not exist. So 1 megavolt, you imagine 1 megavolt means how many volt it is. See how difficult the output will be. How the insecure the person which is situating in the outside side. Okay, that is will not be possible all the time. This equipment will not withstand that much. So this is practically impossible. By theory we can say that the gain is this much. Normally this much is the gain of the op-amp. By this much of gain we are producing this much of volt means it is practically impossible. So what we are doing, we restrict the output. That is why we are looking into another characteristics, that is called the transfer characteristics, my dears. I will explain now. So next, transfer characteristics. Transfer characteristics. So this is VD and this is V0. For getting a straight line, it is almost difficult for me now. Okay, good. So it is called a plus V sag and it is a minus V sag. So what is actually happening here, my dear? I already told you that in order to produce a very big output means it is practically impossible. It is practically impossible. So what we are normally doing, this output can be restricted in plus V saturation or minus V saturation. That means, suppose I produced a differential voltage like 1 microvolt. Suppose VD is equal to 1 microvolt. Imagine VD is equal to 1 microvolt. Then what will be the output? Suppose 10 raised to 6 is the gain of the op-amp, means open loop gain. Suppose I produce 1 microvolt as the input, then the output will be 10 raised to 6 into 1, right? So it will be 10 raised to 6 into 1 microvolt. So 1 into 10 raised to minus 6. So the output will be what? 1 volt. This is okay. And suppose I produce 2 and this also okay. And maximum I can produce like, see, suppose V saturation is equal to 10 volt. Imagine V saturation equal to 10 volt. So maximum I can produce like, suppose I applied 10 microvolt there. 10 microvolt there. What will be the output? Suppose the input is 10 microvolt. What will be the output, my dear? So 10 microvolt, that is 10 into 10 raised to minus 6 into 10 raised to 6. So maximum I can produce 10 volt. Maximum I can go there. So this will be 10 volt. After that, if you increase any voltage, that means if you increase the difference between V1 and V2 to any level, the output will be saturated. That will be maximum plus V saturation. So it is somewhat safe. We can smoothly operate this. We can use this. No issues there. This megavolt and macro, that range will not be there. So we are safe at all. So this same thing can happen in the negative region also. If you are decreasing the negative voltage like this, maximum minus 10 microvolt you can expect, so that it will produce the output voltage of minus V saturation maximum. So in short, my dears, even though it is having a very high gain, we can't produce that much output voltage. There is 10 raised to 5 or 10 raised to 6 gain is there. We can't produce megavolt range output voltage because that is not unstable. So what we are normally doing, we are restricting the output voltage in between plus V charge and minus V charge all the time. That is a very important thing you have to note from this concept. Is it clear? Is it clear, my dears? Okay. And how many ways we can give the input to the Oppac? How many ways you can give the input to the Oppac? How many ways you can give the input to the Oppac? That means you can give input in 3 ways. Ways of input. So first one, we can give input to non-inverting terminal. And inverting terminal equal to 0 volt. You can give one way as you can give an input to non-inverting terminal and you can ground the inverting terminal. That is one way of connecting the input. Second way, to inverting terminal and non-inverting equal to 0. That means you can give the input to the inverting terminal directly and you can short or not short, you can ground the non-inverting terminal. Third way, to both inverting and non-inverting. Okay, you can give input to both inverting as well as the non-inverting terminal. Okay, and if you give input to non-inverting terminal, if input to non-inverting terminal the output V0 will be positive and that is no phase shift. Is it correct now? Suppose we are giving input to non-inverting terminal, so the difference will be nothing but V1 minus 0. V1 minus V2 na, making V2 0 na, so V1 minus 0 will be surely a positive quantity. A positive quantity output means there will not be any phase shift. We are giving a positive signal, you will get a positive signal, so there is no phase shift. And second case, if input to inverting terminal happens, input to inverting terminal happen, then V0 will be equal to negative. That means 180 degree phase shift. 180 degree phase shift. And if you are giving input to, if input to both V1 and V2, output will be, that is output will be with the phase negative or positive. I can simply like positive or negative depends on the inputs. Okay, so I have already told you that 3 ways you can make the input. So according to that 3 ways, you can, the output also you can predict. If you are giving input to the plus terminal only and negative terminal is short, I mean grounded, that means 0 volt. What will be the output? The output will be simply positive quantity. That means A times this V1 will be the output. That also I can write. V0 is equal to A times V1. Here V0 equal to minus A times V2. And V0 will be equal to A times V1 minus V2. That's all. That also you can write. So if you are giving input, if input to inverting terminal, then there will be definitely negative will be the output. That means if you are giving input to the inverting terminal means non-inverting terminal always grounded. If you are giving one input, other will be grounded. That is the concept. That is in that way we are using the Oppac. And if we are both input here, no problem. If one alone only we are giving input means the other side should be ground to earth or it is 0 volt. Okay. And if you are giving input to both the positive and negative terminal, then the output will be A into V1 minus V2. So if V1 or if V2 is greater than V1, then definitely output will be negative. If V1 is greater than V2, then output will be positive. So depending upon the V1 and V2 value, you can predict whether the output will be what? Positive or negative. If it is negative, means it will be 180 degree out of phase with the input terminal. Okay. So these are the things you have to note down. And finally, we are going to discuss the equivalent circuit of Oppac. This is the outline. So what is the equivalent circuit of Oppac? Equivalent circuit of Oppac. Equivalent circuit of Oppac. So this is what you are seeing inside of an Oppac. That is the equivalent circuit of an Oppac. So in which this Ri is nothing but the input impedance, and the output will be nothing but, my dear, A into Va will be the output. We know that now. Output will be A times the input voltage. Input is nothing but the difference V1 minus this is Vd. So simply I can write like A into Vd also. That is the correct thing. Confusion will not be there. So the output will be nothing but A times Vd will be the output. Vd is nothing but V1 minus V2. Okay, V1 is, and R0 is the output impedance. So this is the equivalent circuit of an Oppac. So now we are going to discuss about characteristics of an ideal Oppac. This is a very important question, my dear, very important concept, and definitely you can expect 1 mark from this. Definitely you can expect 1 mark. In the electrical inspectorate examination, it is directly asked, right? 1 question it was there. So characteristics of an ideal Oppac. So ideal Oppac means, my dear, I will tell you one by one. I will tell you one by one. 0 output impedance. 0 output impedance. That means the output impedance of an Oppac will be 0. That means why it is 0 means, suppose some resistance is there, you imagine, suppose some resistance is there, non-zero resistance is there. Then what happen? A portion of A into Vd will be dropped across here. Suppose you connect a load here, my dears. Suppose you connect a load here, it will absorb, it will draw some current now. So due to that current, what happened? A portion of the A into Vd will be dropped across here, and only remaining will be available across V0 as V0 across RL. Is it good? No. So normally we design that Oppac in such a manner that its output impedance will be 0 for ideal Oppac, for ideal case. And input impedance equal to infinity. Another important characteristics of an ideal Oppac is input impedance is infinity. I will tell you that also. This is the input impedance, my dear, Ri. If there is no such impedance, if there is the input impedance equal to 0, you imagine. It is not equal to infinity, is 0. Suppose 0 means it is suddenly short circuit condition now. Ri equal to 0 means what? It is short circuited. If it is short circuited means the V1 and V2 will be not distinguishable. Are you getting my point? If there is no output impedance or input impedance is infinity means it is like an open circuit condition. Only if it is open circuited condition we can distinguish V1 and V2. Otherwise, if it is short circuit condition or Ri equal to or the input impedance equal to 0 means what? It is like there is no distinction of these V1 and V2. That means if it short circuit means there is no difference between this V1 and V2 happens, definitely. It is short circuit means it is simply like a short circuit condition. It is like V1 and equal to V2 happened there. If you apply V1 here, apply V2 here, it is simply connected by a wire. What happened? Suddenly a short circuit happened, and if the V1 and V2 difference is very high means the wire will burn for very short duration of time. Is it clear? Because what? It is actually not happened, because by short circuit means we are making this potential and this potential 0. How that happened? For very fractional second of time, a very high current will flow and that will break the conductor. Is it clear? So if you give some potential difference here by short circuiting the terminal, a short circuit will happen and it will vanish, it will burn. Are you getting what I am saying? You simply take a conductor and take plus terminal here and minus terminal, you connect simply by short circuit means spark will happen, your phase will go down because high current will be flowing, your phase will go. Correct now? So that case will happen here. So always the input impedance will be infinity. Is it called? Is it clear? So next one, infinite bandwidth. Infinite bandwidth. That means this op-amp can carry a signal from f is equal to 0 to infinity hertz. This signal, this op-amp can carry signal at any range of frequency, that infinite bandwidth. Next one, infinite slew rate. Infinite slew rate. I will tell you what is the slew rate means. See my dear, suppose you are giving the input as a square wave. The output also will be another square wave will having an amplified version. Am I right? See here, this is 0 volt and this is suppose 5 volt. This 0 to 5 volt happens in input in 0 second. Am I right? Suddenly it is goes to 5 volt. Means in 0 second it's happening. That same thing will be happening here also. The 0 to 5 volt will be not 5 volt, it will be 15 volt. Suppose the gain is 3. You imagine simply, okay, simple imagination. Suppose it is 0 volt to 15 volt happen in 0 volt. That means there will not be any lag of output voltage with respect to the input volt. That means if it is happening from 0 to 5 volt in 0 second and this happen in 3 microseconds means there will be a small deviation. There will be a small deviation. That means slew rate is nothing but, my dear, the rate of change of output with respect to the input is called a slew rate. So normally it is represented in volt per microsecond. Its unit will be volt per microseconds. These things now we will discuss later in very detail. Don't worry. Just as a characteristics, no? Our heading is characteristics on ideal op-amp na. So simply you note down, and it is infinite slew rate. Infinity means whatever be the time, whenever the input is changing, at the same time the output also is changing. It having infinite capacity to produce output. That is the meaning. It having infinite capacity to produce the output as connected to the input. That means whenever the input is changing that much fast, means the output changing also that much fast. There will not be any lag between the output produced with respect to the input. That's all. That's the concept of infinite slew rate. Next one, infinite CMRR. Infinite CMRR. CMRR is nothing but, my dear, differential mode gain divided by common mode gain. These things also I will explain later, don't worry. Don't worry, I will explain this in detail. Okay, CMRR and related problems, so we will discuss later. But as far as now, I will give a brief idea of what is CMRR means. CMRR means, suppose we are giving two input. Okay, two input terminal now. We are giving two input and we will produce output. Suppose I am giving 5 volt here and 5 volt here. What will be the output, my dear? What will be the output? The output will be the difference in these two multiplied by the gain. Am I right? So the output will be normally what? 0 volt. For an ideal op-amp, it will be 0 now. And suppose I produce 8 volt here and 5 volt here, means the output will be 3 times 8 minus 5 is 3 into A gain. That much will be the output. So what will be the gain when it is in differential mode and what will be the gain when it is in common mode? The ratio, that is AD minus AC. So now in the case of this will be 3A divided by 0, which is nothing but infinity for an ideal op-amp. But in practical case, my dear, even though if you are applying same input here and same input here, there will be a small output voltage due to the imperfection in the circuitry, because we can't make two transistors same as. We can't create two transistors same property, same alpha, same beta, same temperature, leakage current, etc. Now that parameter we can't made exactly equal. There will be a small deviation, that small manufacturing deviation, because it is man-made. It's man-made or robotic, anything. We are giving a material and it will make. So it is a makeable thing, right? So it will not replicate like exactly same. So what happened? There will be a small deviation with respect to one transistor to another, even though it is same capacity, same rating, everything, same material, silicon, suppose. Then also its characteristics will be small, difference will be there. That small difference, because inside this all contains so many transistors. So what happened? Due to the imperfection in manufacturing, what happened? There will be always some difference. That difference will create what, my dear? Even though we are giving same input here, ideally the output will be 0, but practically it won't happen. So ideally this will be infinity, that I already discussed now, but practically it won't be infinity. There will be some output value, even though the common signals are given is 0. That is called the common mode rejection ratio. So the capacity of an op-amp to reject the common mode signal, is called common mode rejection ratio. Which means what? If you are giving a common mode signal, that means both the input are signal same. The output will be what? 0. That means it won't produce any output. It will reject the input. If you are giving same input in non-inverting as well as inverting terminal, its output will be 0. It implies that what, my dear? It rejected the output. It rejected the input. My output is 0 means what? I am producing simply 0. I am idle now. What it means? Even though the teachers called me, even though my parents called me, even though my parent beat me, I am in neglecting mode. I am neglecting that. That is why I can't change anymore. Right now, that is why I am stand still like this. I won't create any emotion. I won't cry. Which means what? I am neglecting everything. I am neglecting my parental scolding. I am neglecting my parents beating, etc. or teachers scolding, etc. So neglecting, the capacity to neglect or the capacity to reject the common mode signal or both the inputs same signal is called the common mode rejection ratio. Normally it will be equal to infinity for ideal op-amp, but practically it is very high but not infinity. Is it clear, my dear? Is it clear? Okay. And another characteristic is nothing but, my dear, another characteristic is nothing but infinity gain. Another characteristic is nothing but infinity gain. Okay, another characteristic is nothing but infinity gain, that its output by input ratio will be infinity. Infinity gain it will produce, infinity gain it can produce. Is it clear? Okay, and it, suppose, that's all, simple. So these are the ideal cases, ideal characteristics, my dear. Please mark up this, you will definitely get one. I will tell you a wonderful trick for that. So characteristics of an ideal op-amp means, except the output impedance, everything will be infinity. So mark it like, except Z0, that is the output impedance, all equal to infinity. So you make it in a box and you can easily see. Here it is 0 output impedance. Rest of all will be half. See, infinity, infinity, infinity. Now. So in that way you can remember this. In that way you can remember this. But in practical case, my dear, this is not exactly true. In the case of practical, op-amp, 0 output impedance will not be there, but output impedance in practical case will be. So here I am representing practical. So practical case, it will be in ohms. In ohms will be the output impedance. Input impedance will be in mega ohm range. And infinity bandwidth also in megahertz range. And infinity slew rate. Infinity slew rate means this is also very high quantity. CMRR is also very high quantity, but not infinity, but very high. Okay. And gain also infinity actually normally, but we will get a very high gain. Okay, that's all. So this is around the picture of the ideal op-amp. Okay, my dear. So that's all about the basics of an op-amp. Okay, in the next class we will learn about the inverting amplifier and the concept of virtual ground. Okay, so until then, bye, take care.